We look now to how we start new configurations. Once the final sequence, which is VA, is decided in configuration CI, and it is in a persistent store by one process, for example, P. So once it is there, we can then start the new configuration CI plus 1. This is because now we have the final sequence, and from it we can start executing in the next configuration. We say that CI has stopped, and stopped means stopping accepting new commands. What is the stop sign? The stop sign that we discussed in the previous unit has complete information about configuration CI plus 1, the new configuration. It knows it has information about the set of processes in the new configuration, the new configuration number, which is higher than the previous configuration number, and the replica's ID for each process Pj in the set of processes for the new configuration. It is the replica's identifiers for J in this new configuration. Each correct process that is going to move from one configuration to the next one, moving from CI to CI plus 1, waits for its replica in the I's configuration to decide its final sequence before taking over the final sequence in configuration CI as its initial sequence in the new configuration. And each correct process Pj that is not in configuration CI, this means it is a completely new process, it could be on a completely different machine, copies each initial sequence sigma I from the persistent store. So in this way we start the new configuration by having replicas in the old configuration handing over information to replicas in the new configuration for the same process, and having new processing starting new replicas, and these replicas gets its information from the persistent store. So now each process PI starts its own new replica. It has all information that's needed for that. And for each replica, as I said, the final sequence in CI is automatically accepted at round 0 of CI plus 1. So round 0 in each configuration is now special. Round 0 copies the final sequence in the previous configurations. So instead of starting from the empty sequence, we're starting now from the final sequence of the previous configuration. Other rounds work as normal. And in a leader-based consensus, each configuration has its own leader election abstraction. This is very important, that we don't mix leader elections in two different configurations. And the leader election abstraction starts for the new configuration when the configuration starts. So you can actually start the leader election abstraction early, and the instances, the replicas that comes in, can catch on later. Leader elections should be able to be tolerant to delayed instances of replicas in that configuration. So let us see now an example here. So now we are in configuration 1, and this is process P1, which is replica 1.1. It is process P2 with its replica 1.2, and so on. So the initial sequence here is the final sequence that we had from the previous configuration. This example continues the previous example, and here you can see something interesting, which is that we are now running process P4 instead of process P3. So it means in this configuration we removed P3 and added P4. The execution in the new configuration continues as usual. We started from here. We continue as usual by extending the sequence of commands. And here's an example where we try to extend the sequence by C4, but this sequence does not have a majority that support it. So here comes a new leader, and just extended the last chosen sequence, which was this sequence, the longest chosen sequence. And it continues like that. So nothing special is as normal. I just want to stress that we can now have overlapping configurations and also overlapping multiple leader elections. And this you can see here. So what do we have here? We have three processes, P1 to P3, in an old configuration. And this configuration will change to another configuration which has 5 processes. So we include also P4 and P5. So the old configuration is in blue and the new configuration is in yellow. So in a situation, for example, where P3 at this point has obtained a final sequence and then it created its new replica and continued to run in the new configuration with the final sequence. This old configuration is the initial sequence in the new configuration. The black boxes here present a situation where both configurations overlap, and if we use P3 as a leader, then it is a leader in 2 configurations. But observe, it's a leader in 2 configurations, but with different replicas. So the replica instances in the blue configuration is actually different from the replica instances in the yellow configuration. We can see now that P1, P2, and P3 are active in 2 configurations and 2 elections. An interesting point is P3 defines really when a new configuration starts. Why is that? So even if we started P4 and P5 earlier, like here, they are not able to obtain the final sequence of the previous configuration before P3 does that. P3 is the one that creates the final sequence of the previous configuration. So P4 and P5 cannot start until P3 enters the new configuration. Depending on the exact sequence consensus algorithm, is it sequence Paxos or Raft, replicas in the old configuration terminate only when P1 enters the new configuration. At this point, there is no need for any of the replicas in the old configuration. We can see the whole sequence of configuration as one ballot array, and this ballot array observes the invariant that if a sequence is chosen in one round number, it is an extension of previous round numbers as follows. That is what we are going to show now, and this shows that our configuration method is safe. So the round numbers can be extended to be a pair. This pair, an increasing configuration number and a local round number. So C, again, is a configuration number and is a local round number within that configuration. And since configurations are totally ordered, rounds are also totally ordered across configuration. So this is an interesting observation. But let us see this here. So here is a situation where now the round number is both a configuration number and a round number, a local round number. And this is the final sequence in configuration C0. And now we move to a new configuration. The final sequence is the initial sequence, but this round number is higher than this round number because Ci is higher than C0. And as we can see now, we can see everything works as if we are just doing one ballot array. And as usual, a sequence is chosen if there is a majority supporting that sequence and it is in a higher number than previously chosen sequences. So a process has replicas in multiple configuration, but can only be running in one configuration. It is still helping the other previous configurations, but it is running in one configuration. It is helping in a sense that it is participating in the election of previous configurations, but it is only running in one configuration. And by running, I mean it is extending its sequence in that configuration. Starting and stopping configuration, CI is not coordinated between processes. So a process PI may have a stopped replica in CI-1. It is there still, helping other replicas to reach the final sequence in CI+1, and it can be running in CI. And a process PI may have a replica in CI+1, but it didn't start yet, because to start, the replica in CI has to deliver the final sequence in that configuration. So here is our situation. If we look to process P, this is process P running here. So a process P may act in multiple replicas in different configuration. P is stopped here. So this is stopped. P is running here. This is running. And P did not start here. Even if this configuration is running, I mean, in a sense that these replicas are in the running state and they are adding commands. In this case, the replica of P1 here is a minority, so this consensus can proceed. Let us discuss handover now. So as soon as a proposer, P in CI, learns that the final sequence in CI is chosen, then P could inform replicas in CI+1 about this sequence. So you could think of a situation where we have created the replicas for the next configuration, but still waiting to be informed by a proposer or a leader or a replica in the previous configuration. This happened before, if you remember the picture, where we had overlapping configuration and the yellow new replicas were waiting for the blue replica to get the final configuration. So that the replicas in CI can start and maintain availability. A process that acts as a replica in both CI and CI+1 will learn this sequence through normal decide messages, and as we said, other processes in CI+1 also learn this. And this either from a store or by sending additional decide messages to them. There are a few optimizations that could be done. The first optimization is what we call early sequence transfer. So these are not part of the correctness of the algorithm, but it is just optimization. As a leader, P receives a proposal with a sign command. So one possibility for P is to defer this command for a while, is not to issue the sign command immediately, which would mean it can still accept other commands from the clients instead of rejecting all commands. Instead, that process P starts to update the replicas in CI with the longest sequence decided so far, and then only accepts the stop sign command once the replicas in CI are sufficiently up to date. In this way, we make the interruption of the service minimal. Of course, there is a trade-off, and the trade-offs are basically we don't want the system in this configuration CI to stay so long there because maybe it is in a critical state. What I mean by critical state, that it's only 2 out of 3 are living, and if one process is delayed, it might also die. So there's a trade-off. We cannot wait too long because processes might fail and we cannot continue. Another issue is that if a new replica process is introduced in the system, then the entire sequence has to be transferred to P. We are going to discuss 2 ways to do this now. And this, of course, might take time because this sequence might be a very long sequence. So dividing the sequence into chunks and letting other processes in the same configuration send the chunks in parallel, this might increase efficiency. Again, it's a trade-off between the network capacity and processor load. Much more important and necessary optimization is the so-called snapshots. So currently, the entire sequence of commands must be transferred from a configuration to the next one, especially when new processes are introduced. One possible way to avoid this is to compact the log or the sequence. And of course, you do this by basically taking a snapshot of the state of the replicated state machine. So it means now, instead of having, for example, say, this sequence of command C1, C2, C3, and this is the third command, then you can instead having the state after executing this is the state, call it S after executing the three commands, and saying this is the log until the slot number 3 or the item number 3 in the sequence. Okay, you can do this regularly, for example, after every 1,000 command or every hour, and therefore then you can garbage collect the prefix of the sequence. There's an important issue which we did not discuss, and I will mention it now, is that by doing this, we don't know what kind of commands have been executed from the point where we compacted the log. This means we cannot search the log to see if a command instance has been already existing there, and if we don't want to do it twice or want to avoid duplicates. But one solution is that you store the last command of each client executed by the state machine with its results. And if this command comes again to the replicated state machine, it knows that this is repeated and only returns back only the result. This assumes that the clients are sequential. You can execute one command at a time, send the command, wait for the answer, and then execute the next command. The most important thing is to find a method that you could use to take care about preventing duplicate commands. Here is another optimization to speed up things. The optimization goes like this, that what we have been explaining until now is that we let each replica continue execution as normal until it comes to the stop commands, and this terminates basically the execution of the replica here, and it gives its process the ability now to restart a replica in the next configuration. There is another way to do these things, which is what I call here, if you have a leader in a prepare phase and this leader is in configuration C, it sends prepare message to all replicas in CI, and then for each process Q we are going to have three cases. Either the process and its replica is running in this configuration, so things behave normally. Either the process's replica hasn't started this configuration yet. The process then Q obtains the final sequence from P and immediately starts the replica CI and sends a promise to P within the new configuration. This is basically saying, okay, I don't wait for my replica. I have already got the final sequence from the leader, and I can just continue to the next configuration. There is also a possibility for the inverse situation, where a leading process starts to prepare a command, and he sees that Q has already stopped in CI. And when he adopts the sequence coming from Q, because it will do that in the prepare phase, then Q can send the sequence in CI to P, after which P will also stop and starts its replica in CI +1. As we know, in both case 1 and also in case 2, P, if he is still the leader in this new configuration, then he has to wait for a majority of promises, but this is understood. So in summary, reconfiguring a replicated state machine is relatively straightforward process. Round numbers are extended so that the round numbers of earlier configuration are ordered before the round number of later configuration. This is important to know. At most, one of the replicas that a process implements may be running at one time, and running means accepting commands and increasing commands. And handover procedure is important to get availability and efficiency, as we just discussed.